concurrent execution of CPUs and other controllers and other devices, concurrent execution of CPUs and other devices concurrent execution of CPUs and other devices will lead to competing for memory access, will lead to competing for memory access. So look at the figure. So we may have two or more processors also at the time. And if you imagine that the processors as well as the keyboard, monitor, and one of the disk controller all needs a memory at the same time. So then what will happen? Then the memory will be required by all of the devices at the same time. That is what I'm trying to say. Next, I/O devices means what? Input output devices. What are the input output devices in this controller, in this diagram? Mouse, keyboard, and printer. Okay. So I/O devices and CPU can execute concurrently. I/O devices and CPU can execute concurrently. I/O devices and CPU can execute concurrently. Each device controller is in charge. Each device controller is in charge of a particular device type. Each device controller is in charge of particular device type. And each device controller has the local buffer. And each device controller has local buffer. So look at the device controller which is there, like the disk controller, USB controller, or the graphics adapter. They have the local buffer. Local buffer means what? A buffer which will make the input to be queued, and this device controller will take each and every input one by one, and then it will process. Similarly, for the output, will have this buffer. Okay, CPU moves the data. The CPU moves the data. To or from the main memory. CPU moves the data to or from the main memory or to or from the local buffers, or to or from the local buffers. Divishti Raghu, don't join the class late, okay? Better not to join.
Sorry, sir.
Okay, it's highly interrupting. Just now I said to come late, and it's applicable for all. Better not to join if you are joining late for my class. Highly irritating, you know.
Sorry, sir. This is the last time.
So CPU moves the data to and from the main memory and to and from the local buffer. The device controller informs the CPU. The device controller informs the CPU. The device controller informs the CPU. The device controller informs the CPU that it has finished its operations. Device controller informs the CPU that it has finished its operation by causing an interrupt. By causing an interrupt. So imagine that. So we'll discuss now whatever I just given a note. We'll discuss it. So imagine that the memory has been occupied by any of this device controller. Either it may be input-output devices, or maybe the graphics adapter, or it may be some of the other disk controller. Imagine that its memory has been occupied, and the CPU has been waiting for the memory. So since as memory has been occupied by this device controller, the CPU will be waiting for the memory. So once the device controller has done its job, somehow it has to communicate with the CPU that it has done its job. So this communication from the controllers to the CPU will be caused by an interrupt. So we discussed in the last class what is an interrupt. So what is an interrupt? We discussed in the last class. Can anyone tell me? That is what we stopped with.
It's a process executed by CPU when a user requests for another process.
Okay.
Then create a disturbance.
Exactly. So it is applicable for the CPU as well as for other. So whenever a process is being executed with the CPU, and when a user requests for another process, then it will create a disturbance for the running process. Then it will cause an interrupt. So with that, have we discussed this in it? Have we discussed this hardware interrupt and software interrupt?
Yes, sir, we did.
Okay, now write a trap. Have we discussed a trap?
No, sir.
Okay, write heading as trap. Have we discussed a system call?
No, sir.
No, sir.
We didn't discuss. Okay. So where we stopped exactly? Can you tell me the line? Interrupt can occur for either from the hardware and software. Have we discussed?
Sir, we stopped software may trigger an interrupt by executing a special operation called system call.
Okay.
And that's it. We didn't explain system call.
System call, that will be explaining the glucose of that. Okay, please write this. Events are almost always signaled by the occurrence. Events are almost always signaled by the occurrence of an interrupt or a trap. Events are almost always signaled by the occurrence of an interrupt or a trap. Events are almost always signaled with the occurrence of an interrupt or a trap. A trap is a software generated interrupt. A trap is a software generated interrupt. A trap is a software generated interrupt caused either by an error or by a specific request. Either by an error or by a specific request from a user program. I'll repeat, a trap is a software generated interrupt caused either by an error or by a specific request from a user program. A specific request from a user program. When CPU is interrupted, it stops what it is doing. When CPU is interrupted, it stops what it is doing and immediately transfers its execution and immediately transfer its execution and immediately transfer its execution to a fixed location, and immediately transfers the execution and immediately transfers its execution to a fixed location which contains the starting address where the service routine for the interrupt is located, which contains the starting address where the service routine for the interrupt is located. The interrupt service routine executes. On completion, the CPU resumes. On completion, the CPU resumes the interrupted computation. So I'll just summarize. So imagine that either it may be the CPU. Imagine that CPU for the case. I will tell this case for the controller in a different aspects after this. Imagine that CPU is executing a program. And somehow it is interrupted. And somehow the execution, maybe imagine that you are executing a program. So CPU executing the program line by line. So that is how the CPU executes the program. And somehow in between, the execution is interrupted. So on this interruption occurs, what does it do? The execution, the controller, okay, the CPU execution is stopped. The program execution is stopped in between. And it will immediately transfer the execution to the interrupt. So where that transfer will go? So immediately imagine that you are executing a program which contains 10 lines. You are executing 5 lines. 5th line, you are in the process of executing the 5th line. Suddenly the interrupt comes. So what does it do? The control will transfer from the CPU to the interrupt. So this control now from the 5th line of the program, it has to go somewhere. Where it will go? It will go to the starting address of the service routine for the interrupt. Immediately on occurrence of the interrupt, the 5th line will not be executed in the CPU. The program 5th line will not execute that. Instead, the control will now transfer to the starting address of the interrupt. So now the control will go to the interrupt. So the interrupt will gain the control and will try to completely execute the interrupted job. It will complete the execution of the interrupted job. After the interrupt job has been completed, again the control will again transfer to the 5th line of the program. Understood or not?
Yes, sir.
Yes, sir.
After the interrupt completes its routine, it will just come to the CPU and then it will start the execution from the place where it has left. So already I said it is the process of executing the 5th line. Now after the execution of the interrupt, now it will start executing the 5th line and will complete the execution. It is similarly applicable for other controller also. Just now I have discussed, while discussing this diagram I have discussed. See, once the controller is given to any one of the interrupt, like USB controller or the graphics adapter or any other disk controller, once this execution has been taken place, once the controller taken over the control, after the control, for example, imagine that the keyboard has taken the control. After the keyboard finished its job, through the USB controller, it has to inform to the CPU that it has finished its job so that the CPU will continue the execution. That is also being done by the interrupt. That is what I said. The device controller will inform the CPU that it has finished its operation by causing an interrupt. So 2 things you understood here. While executing the program, when we get an interrupt, the control from the program will be given to the interrupt, and the interrupt will give the controller to the starting address of the interrupt program. And once executing the interrupt program completely, again, it has to hand over the control to the CPU. So both the things we need to have an interrupt for the smooth functioning. IO devices, please continue. IO devices and a CPU can execute concurrently. That is what I said in the beginning of the class. IO devices and CPU can execute concurrently. Each device controller is in charge of a particular device type. Each device controller is in charge of a particular device type. It may be repetitive, plus please write. Each device controller also has the local buffer. Each device controller has a local buffer.
And sir,
Please, just a second. Device controller informs the CPU. Device controller informs the CPU that it has finished its operations. Device controller informs the CPU that it has finished its operations by causing an interrupt. The interrupt transfers the control. The interrupt transfers the control interrupt transfers the control to the interrupt service routine. The interrupt transfers the control to the interrupt service routine, generally through interrupt transfers the control to the interrupt service routine, generally through the interrupt vector, which contains the address of all the service routine, The interrupt architecture must save the address of the interrupt instruction. The interrupt architecture must save the address of the interrupt instruction. A trap or an exception. A trap or exception is also called as exception. Is a software generated interrupt. Caused either by an error or a restore request. An operating system is an interrupt driven. Please write the heading as interrupt handling. So until then, 2 points you should be getting now. One point is that whenever CPU is executing a program, it can be always transfer its control to a separate routine to occurrence of an interrupt. When a CPU is executing the program, it can be interrupted, and once the CPU on execution program, if it is interrupted, the control from the program will be transferred to the interrupt service routine. Where is the interrupt service routine located? Again, it will be located in the memory. So the control will be transferred from the program which is in the execution to the starting address of the interrupt. And another thing you should also imagine that whenever a control has been given from the CPU to other devices. The other devices may be like keyboard, mouse, printer, or monitor. Once the job has been executed, the particular device controller again will cause an interrupt to intimate the CPU that it has completed its job. So those things, if you understood, then we can proceed further. Right, heading as interrupt handling. Interrupt are a part of computer architecture. 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 Each computer design has its own interrupt mechanism. Each computer design has its own interrupt mechanism, but several functions are common. Irrespective of the computer design, the interrupt must transfer. Irrespective of the computer design, the interrupt must transfer the control. The interrupt must transfer the control to the appropriate interrupt service routine. The interrupt routine is then called indirectly. The interrupt routine is then called indirectly. The interrupt routine is then called indirectly through a table. The interrupt routine is then called indirectly through a table which holds the address of interrupt service routine, for various devices. This array or interrupt vector of addresses. This array or interrupt vector of addresses is then indexed by a unique device number. This array or interrupt vector of addresses is then indexed by unique device number to provide the address of the interrupt service routine. Provide the address of the interrupt service routine for the interrupting devices. The main concept is that whenever the interrupt occurs, the control from the CPU will directly go to the starting address of the interrupt service routine. Okay, so here there will be, as I said, there will be various device controllers. So that will be causing the interrupt for execution of the CPU. So there will be either an array or it will be an interrupt vector of address. So this interrupt vector of address will contain the unique device number which will provide the address of the interrupt service routine for each of the interrupting devices. Next, right, I/O interrupts. To start an I/O operation, I/O means input output. To start an I/O operation, I hope you are all continuing, right? You are all in line with me.
Yes, sir.
Yes, sir.
To start an I/O operation, the CPU loops to start an IO operation, the CPU loads appropriate registers. To start an IO operation, the CPU loads the appropriate registers within the device controller. To start an IO operation, the CPU loads the appropriate registers. Yes. To start an IO operation, the CPU loads the appropriate registers. The CPU loads the appropriate registers within the device controller. To start, and I will repeat this, to start an IO operation, the CPU loads the appropriate register within the device controller. The device controller in turn examines examine the content of these registers. The device controller in turn examine the content of these registers. The device controller in turn examines the content of these registers to determine what action to take. Example, if it finds a read request, for example, if it finds a read request, the controller will start transfer. For example, if it finds a read request, the controller will start transfer of a data. The controller will start transfer of a data from the device to its local buffer. If it finds a read request, the controller. Here the controller means device controller. The controller will start transfer of the data from the device to the local buffer. Once the transfer of data is complete, the device controller will inform the CPU. The device controller will inform the CPU that it has finished its operations. The device controller will inform the CPU that it has finished its operation. Again, this will be done by the interrupt. This situation will occur. This situation will occur in general. This situation will occur in general as a result of user process. This situation will occur in general as a result of user process requesting IO. Once the IO is started, two course of action are possible. That is, IO started and IO completed. When I say IO, you have to write I/O, which is nothing but input output. Okay. Once the IO is started, two course of action are possible. First one is IO started, and second one is IO completed. This is known as synchronized IO. So I will just explain what I'm dictating so far. Imagine that I will take a program under execution. Imagine that the CPU executing a program, and suddenly somewhere in the program you want an input from the user. Imagine that you are executing a program which will check whether the given number is a prime or not. So imagine that you are executing the program, and somewhere while executing the program, you encounter a line which asks an input from the user, So when a program is under execution, it will be under the CPU control. So CPU executing, and somewhere it encounters the input from the user. So whenever it encounters a line which is requesting an input from the user, the control from the program, the control from the CPU, now it has to be transferred to the input device. So that will again caused by an interrupt. So again, the control has to be transferred from the program, it has to be now transferred to the input device. So this will be caused only by an interrupt. So now the control will be in the keyboard. Imagine that you are demanding an input from the user. Now the control will be now handed over to the keyboard. Once the user has given an input, again the control now it has to be transferred from the keyboard, it has to be transferred to the CPU. Again the transfer of control from the keyboard to the CPU will be happened by the interrupt. So if you look now, there are two interrupt occur. The first interrupt occurs whenever the CPU reads a line which is requesting an input from the user. That again now after reading the line or input which is requested from the program, the control now has to be transferred from the CPU to the keyboard. So that transfer will take place only with the help of an interrupt. Again, when the user has given the input to the program, or whenever the user has typed an input in the keyboard, again the input, after giving the input by the user, the control again has to be transferred from the keyboard, again it has to be transferred to the CPU. Again that will cause by the interrupt. So there are two interrupt occur. One interrupt will be occurring transferring the control from the program to the keyboard, and another interrupt will occur whenever transferring the control from the keyboard again back to the CPU for execution. The two interrupt will occur. Okay. So that's why I said the two course of action will be there. One is an IO starter and IO completed. So this is known as synchronized IO. Have you understood until now?
Yes, sir.
So what
Yes,
is
sir.
an interrupt? What is an interrupt? Generally, what is an interrupt? I'm asking not with respect to the definition. What you understood, I'm asking from the understanding which you discussed. Can you please tell in your own words what is an interrupt?
The interrupt is like a signal.
Okay, it's a signal. What does it do?
Whenever some program is under execution, then another program will send this signal to CPU to stop the execution of that particular program
Okay.
and start the execution of this new program.
So whenever the signal is given, what does the control from the CPU will now go to the starting address of the interrupt. Understood?
Yes, sir.
Kaushik?
Yes, sir.
Okay. Now control from the CPU has been given to the starting address of the interrupt. So now what will happen after that? No, please, I have discussed this. Please let me.
The interrupt, it will go back to the.
Exactly. After executing the interrupt service routine, again the control has to go back to the CPU for transferring the control from the interrupt service routine. Again, we need to have an interrupt that will transfer the control from the interrupt service routine to the CPU. So the interrupt service routine, it can be anything, like it can be an input which is requested from the user, or it can be like any other interrupt. Until then, it is clear?
Yes, sir.
Okay. So the other possibility is known as, so far now we discussed the synchronized IO also we discussed. So the other possibility is called asynchronized IO. The other possibility is called asynchronized IO. In asynchronous IO, the control is returned back to the user program. In asynchronous IO, the control is returned back. In asynchronous IO, the control is returned back to the user program without waiting for the IO to complete. I'll repeat. In asynchronous IO, the control is returned back to the user program without waiting for the IO to complete. The IO then can continue. The IO then can continue the IO then can continue while other system operation occurs. The IO then continue when other system operation occurs. So there are two IO we discussed. One is a synchronous IO, other is the asynchronous IO. In synchronous IO, what will happen? Whenever the control from the program has been passed to the IO device, only after the user has given an input, the control again will be given to the program. That is called synchronous IO. There is another kind of IO known as asynchronous IO. In asynchronous IO, what does it do? Once the control has been transferred from the user program to the input-output devices, even if the user has not given the input, the control will again back to be given to the user program. That is called asynchronous IO. So in that case, what will happen? The input will not be transferred from the keyboard to the user program, because it is not waited until the user has completed his input. Even before the user has given the input, the control will be transferred from the keyboard to the CPU. That is called as asynchronous IO. In that case, the complete input which is given to the user will be transferred to the user program only when other kind of system operation occurs. Please write, after the IO starts, after the IO means input output. After the IO starts, the control returns to the user program. After the IO starts, the control return to the user program. After the IO starts, the control will be returned to the user program only upon the control will be returned to the user program only upon the control will be returned to the user program only upon IO completion. The control will be returned to the user program only upon IO completion. The control will be returned to the user program only upon IO completion. And then the following actions may occur, and then the following actions may occur. First point, wait instruction idles the CPU. Wait instructions idles the CPU until the next interrupt. Wait instructions idles the CPU. Wait instructions idles the CPU until the next interrupt. Second one, it will be in the infinite wait loop. It will be in the infinite wait loop. Third one. At most, one IO request. At most, one IO request is outstanding. At most, one IO request is outstanding at a time. At most, one IO request is outstanding at a time. No simultaneous IO processing. So imagine that CPU is executing a program, and somewhere the program is requesting user input. So the CPU will transfer the control to the interrupt routine. That is nothing but the IO interrupt. So it will give a control to the interrupt routine. So now the control from the interrupt routine will be given back to the CPU only after the completion of IO. But in some cases, it will take much longer to gain the control. It will take much longer to transfer the control from the interrupt to the program which is under execution. So what will happen if what cases might have happened if that is a delay from the control which is given in the interrupt to given back to the program? There may be many possibilities. One possibility is that the user may not give an input for a longer period of time. So imagine that you are writing a program to find whether the number is prime or not, and then somewhere you return an input request in the program. So the control from the CPU will now transfer to the interrupt service routine. So now the control will be given to the interrupt service routine for the program to get an input from the user. So if the user has not given the input, what will happen? The CPU will be idle until the input will be given from the user. Unless otherwise the user gives the input, the control will not transfer back to the CPU. So in that case, the CPU will be idle. Second, if there is a loop, imagine that while getting an input from the user, imagine that it will be got into an infinite loop. Then what will happen? Again, the control from the input interrupt will not be back to the CPU. Again, the CPU has to wait for that long period of time. Or the third case, what I discussed is that imagine there is a multiple sequence of input-output request, and at least if we don't receive the input for one of the input data, again the CPU will be in the infinite loop waiting for the control transfer from the IO interrupt back to its program execution. So please write this. After the IO starts, so in that case, what will happen? If the input is not given by the user for the infinite period of time, the CPU will be keep on waiting. The CPU time is very precious, because many other programs or many other jobs can be executed when the CPU is idle. So we cannot wait for the input to be completed. Do you agree with me? Because there may be a number of processes in the system which is waiting for the CPU. Because the user program is waiting for the user input, we cannot make the CPU idle. The input may be a short duration or input may be a longer duration. If at all it is a longer duration, then the CPU will be waiting to transfer the control from the input devices back to the program for execution. We cannot afford to wait. We cannot afford to make the CPU idle because CPU time is more demanding by the processor. So we cannot make the CPU idle simply because for the input request or simply because for the input from the user side. So please continue the notes. After the IO starts, the control returns to the user program. After the IO starts, the control returns to the user program. After the IO starts, the control returns to the user program without waiting for IO completion. Without waiting for IO completion in following ways. Imagine that it is an infinite wait. So unnecessarily we cannot wait, we cannot put the CPU idle. So what we can do, that is what we're going to discuss. First one, system call. First one is nothing but system call. Request to the operating system. Request to the operating system. Request to the operating system to allow the user. Request to the operating system to allow the user. To allow the user to wait for. To allow the user to wait for. To allow the user. To allow the user to wait for. To allow the user to wait for IO completion. To allow the user to wait for IO completion. Second one, device status table. Device status table. Device status table contains entry for each IO device. Contains entry for each IO device. Contains the entry for each IO device, indicating its type, address, and state, indicating its type, address, and state. Third one, operating system indexes into IO device. Operating system indexes into IO device. Operating system indexes into IO device table to determine operating system indexes into IO device table to determine the device status, to determine the device status, to determine the device status, and to modify the table entry, and to modify the table entry, to include and to modify the table entry to modify the table entry to include interrupt, to include interrupt, to include interrupt. So what I'm trying to say is that whenever there is an interrupt, especially for the input or input output interrupt, that the system will operating system will maintain a device status table. So in the device status table, there will be many columns, including what type of interrupt, what is the address of the service routine, and what is the state of an interrupt. The state of the interrupt, it will be like ongoing process or it is in wait process. If it is in wait process, what will happen? The control will be there in the IO device controller. It will not be given back to the CPU. If the state is in the wait for a long period of time, what will happen? The OS, it can decide or it can go to the device status table and can change the status of the table. It can change the status of the particular interrupt which is waiting for a longer period of time for the user input to it can change it. Actually, the OS can have the capability to change the device status which is waiting for the user input for a longer period of time. What will happen if it change the status? Again, the control will be given back to the program which is under execution. So that is what we have discussed today. So please write this diagram. We can discuss more that in the next class. Please write this table for this synchronized and asynchronous IO. I have tried to explain that to a diagram. So please draw this diagram. So the left hand side is nothing but a synchronized IO, and the right hand side is nothing but asynchronous IO. So imagine that this is a CPU. The CPU will executing the program. We have an interrupt. We will transfer the control from the program to the interrupt. And once the input operations or any other operations has completed, again the CPU will transfer the control back. Again the interrupt will be transferred back to the CPU, and then the program execution will continue. Whereas in the asynchronous IO, that is not the case. Please draw this diagram. We will discuss that in the next class. All of you drawing the diagram?
Yes, sir.
Please draw the diagram. We'll discuss the diagram in detail in the next class. So we'll discuss in generally how what is synchronous IO and what is asynchronous IO in a much more detailed way in the next class. Now, tomorrow is holiday due to Ambedkar Jayanti. We'll meet again on Thursday. If you complete the diagram, please let me know.
Yes, sir. Answer.
Others?
Done, sir.
Okay, so we'll discuss in detail on Thursday. So please give the attendance in the Google Classroom. Thank you so much.
Thank you,
Thank
sir.
you.
Thank you.
Thank
sir.
you, sir.